let's get started. Composite functions. So write this down. So to compose two functions, means to apply them one after the other. So for example, if f of x equals, let's say, 4x minus 3, and remember from last week it's important that we give a domain, g of x equals e to the x, again, x takes any real number, and the things I'm going to ask us to find: A, find fg, right, I'll probably write find fg of 3, find gf also of 3, then part C, find fg of x. And they're the three things that we're going to find. Now with function notation, basically I think of these functions queuing up to have a go at the 3. So this g gets to have a go at the 3 first. And what g does, because first in the queue, it's the closest to the 3, g takes whatever it sees and e's it. So first in line is g, so we're going to e that 3. But after it's been e'd by the g, the f is still waiting in line. So that f now needs to be applied to e cubed. So f takes whatever it sees, in this case x. So f takes whatever it sees, times it by 4, then takes 3. So that's what's happening here. Timesing it by 4, then taking 3. And that's the answer. I think answers are always better exact unless otherwise asked. So I would always give my answers exactly. Right, so part B, find g f of 3. Well, this time f is the first thing in the queue to have a go at that 3. So f has a go at the 3. So it becomes 4 lots of 3. Take 3. However, it still needs to be g'd. And I think I can do better than this. I think I can simplify that before I try and g it. So g becomes, g takes in 12 take 3, which is 9. So if we g9, g takes anything and e's it. So if we apply g to 9, it becomes e to the power of 9. Done. Then finally, fg of x, it wants it this time in algebra, not numerics. So if we g x, it becomes e to the x. Then f has a go. And f takes whatever it sees, times by 4, then takes 3. Becomes 4 e to the x, take 3. So let's do give you a couple of minutes to do a couple of questions. So I'll take these ones here. So only a couple of minutes we'll spend on this because it's not that challenging a topic. I want to get on to some more difficult modulus stuff. So I'll white out some of the questions. It's just questions A and B that I'd like you to have a try at. from last week, we saw that this notation means f of x equals 4 minus x, that g of x equals e to the x, h of x equals 2x squared plus 7. So have a go at those. As I say, a couple of minutes is all it'll take you. Another minute on that. Right, okay. So let's have a go. So part A. So f of x equals 4 minus x, and g of x equals e to the x. So we're going to find, first of all, gf of x, as it's asked. Well, f gets to go first. When f sees x, it makes it negative, then adds 4. Or you could think of it as taking it from 4. So g of 4 minus x. And here g takes whatever it's given and e's it, equals e to the 4 minus x. And it's said in a similar form, so we should really give back the notation that they use. So in a similar form, gf maps x to e to the 4 minus x, where x can take any real value. And that's the similar form that the question asked for. You'd probably get the marks if you did it in function notation rather than mapping notation, but because it said similar form, we're going to try and give them exactly what they want. So b hg of x, well, g e something, so it becomes h of e to the x, and h takes whatever it sees, squares it, times it by 2, then adds 7, so it becomes 2e to the 2x plus 7. And given it in a similar form to what we wanted, to what the question wanted, hg takes x, maps it to 2e to the 2x, adds 7, where x can take any real number. So typically on the new spec, when we're asked to define a function, yes, so I've had a question, do we have to include the domain? Yes, in the new spec, when we're defining a function, typically they want the domain, and from some of the exam papers I've seen so far and the mark schemes, there are marks for defining the domain as part of the function. Right, let's move on now. So that is composite functions. And there's nothing really much more to that. So I think 10 minutes is enough time. I've put some worksheets in the lesson area that you can have a go at, and I've got full worked solutions. So have a go at those. But it doesn't get any more difficult than what we've just done. So what I'm going to do now is move on to the harder topics, which is the modulus function. So you might have been told that the modulus function makes negative numbers positive, and that's sort of true when we're dealing with real numbers, but really what modulus means is distance from zero, distance from the origin, and that's why we can apply it to vectors as well. So modulus, when talking about vectors, we do Pythagoras to find the distance from the origin. But it is true to say with only real numbers it makes negative numbers positive, but bearing in mind, like for those of you that do further maths, when we've got complex numbers, the modulus of a complex number is also the distance from the origin. As I say, that's the case for real numbers as well, but it helps. It makes it easier if you think of it as just making negative numbers positive. So we'll write that down. So when dealing with real numbers, we can think of the modulus which is also known as magnitude in physics, or absolute value in computer science. And you will see those definitions occasionally in maths. So it's also known as the magnitude or absolute value. You can think of the modulus as making negative numbers positive. But as I say, it really means distance from zero. Right, so for example, and hopefully you find this patronisingly easy, the modulus of minus 2 is 2. The modulus of 2 is also 2. It does nothing to positive numbers. So we'll get straight on to drawing graphs of moduli functions. So graphs of functions involving modulus. Right, so we'll start with an example, and I'll just take you through the steps that I would use. So, e.g., sketch y equals modulus of 4x take 3. So what I would do here, I'd do a rough graph first, then a real graph, and I make it clear that I don't want the rough graph to be marked. So firstly, I'm going to draw the graph of y equals 4x minus 3, forgetting about the modulus sign. So 4x minus 3 would have a relatively steep gradient and would cross at minus 3. So that's my rough sketch there, and mark on the key points. So that would be minus 3, and we need to figure out what that point is there. So 4x minus 3 equals 0, 4x equals 3, so x equals 3/4 would give us the x-intercept, also called the root, so that's 3/4 there. And what the modulus does it makes, as I said before, any negative values positive. So any negative y values will become positive. So the graph will never go below the x-axis. So actually any negative part will be reflected up. So that -3 is no longer -3, it's reflected upwards. And now it's 3. So what I'm going to do now, copy the axes. Move it across there. And actually do my proper graph. And as I say, I'd encourage you to do the same. So in red, here's my proper graph. Get rid of all the features now we don't want. And that there is the graph of y equals mod of 4x minus 3. And just to make it clear to the examiner, we don't want this rough attempt marked. It's just an intermediate bit of work and we're going to cross that out. So the bit that's worth the marks is this bit here. So we'll try and sketch a more complicated one now. Let's try and e.g. sketch y equals x squared minus 9 modulus. So I'll give you a moment, maybe a minute, to have a good sketch in that graph. I'll just get the axes ready while you're having a go. If you're watching the recording back, you might want to pause this now and have a go. Take as much time as you like. So I would say draw the graph without the modulus there, then with the modulus there. So the graph of y equals x squared minus 9 looks like that. And we know the roots are minus 3 and 3. And the y-intercept's minus 9. What happens to this? The negative part is reflected upwards, like that. So, drawing the real thing. Like that. Like that. So crosses, or rather the roots are minus 3 and 3. And now it no longer crosses at minus 9. It crosses at 9. So that's y equals mod of x squared minus 9. And let's cross out our rubbish attempt. So let's try a more difficult one now. Let's say e.g. sketch y equals mod of x minus 3 plus 2. Now I think this is going to take multiple rough graphs because I think this is a multi-stage process. So let's have a look at what we do when there's multiple transformations done. So got that there. So first of all, let's draw y equals x minus 3, which is going to look something like that. And finding the root, we'll see that it's 3 and it crosses at minus 3. But then it's going to be reflected upwards. So like that. So the green graph is the one I'm considering now. We reflected all the negative parts upwards. But then outside the modulus sign, we see that there's a transformation of 2, a translation of 2 units in the y direction. So then this green graph is then lifted 2, 1, 2, like that. So applying them in the order stated, we end up with that graph there. So let's draw our neat version now. So we see that it looks like this here. And let's mark on that minimum point. So the minimum point was 3, 0 originally, but we've lifted it 2. We've translated it 2 upwards. So now it's 3, 2. And before we'd reflected it, and let's put that original graph back down there, show the multiple stages. So before we'd translated it, that there would have been 3. Then it was lifted up 2, translated up 2, which means that that is now 5. So that's all the key features of that graph. So do it in multiple steps. So how about I'll try and give you 2 more graphs to sketch. See how we get on with them. So e.g. sketch y equals mod of 16 minus x squared and y equals mod of, let's say, 10 minus 3x minus x squared. So have a go at sketching those 2. Take a couple of minutes. So I'll just get the axes ready. So 16 minus x squared. It's a minus x squared graph translated upwards 16. And 4 and minus 4 are the roots. And the shape of this is really, really important. It needs to be pointy, like that. So this part needs to be reflected upwards. This needs to be symmetrical through the x-axis. Let's draw the proper one. You'll see it's like this here. And I can do better than that actually. Have another go at that. It's better. And make it pointy like that. -4, 4, 16. Labeling it clearly. Y equals mod of 16 minus x squared. Cross that out. We don't want that marked. And let's try the other one now. Y equals mod of 10 minus 3x minus x squared. Now I think there's a little bit of work we can do to this to make it look a bit nicer. More like a quadratic that we're used to seeing. So I'm going to write the terms in the order that I'd expect to see them. So minus x squared minus 3x plus 10. And I'm going to take out a factor of -1 in there. So equals the modulus of minus x squared plus 3x minus 10. Like that. Equals, let's try and factorize it. Modulus of minus, and it should factorize x plus 5, x minus 2, x plus 5, x minus 2, and there we're ready to sketch it now. So it's a negative quadratic that has roots at -5 and 2, like that. -5, 2. Y-intercept at 10. And any negative part of the graph is reflected upwards, like that there. So we're ready to draw the real thing now. Going straight from our rough answer. So that's 10 minus 5 and 2. And that's the graph of y equals 10, the modulus of 10 minus 3x minus x squared. So they're the steps you have to follow. And the reason I put such emphasis on sketching these graphs is because we're going to now use this method to try and solve equations, because it's my firm belief that this one-size-fits-all method of drawing sketches of the graphs first before trying to solve equations actually works out a lot easier than doing it otherwise. So put a subheading, solving modulus equations. And the worksheets that I've put in the lesson area cover all of this extensively. So there's loads and loads of practice you can do after this lesson, and keep playing the recording back. It'll be uploaded within about an hour of the lesson finishing. So solving modulus equations. So let's say, start with an example, e.g. solve, I don't know, modulus of x minus 5 equals modulus of 7 minus x. And I'm going to do this using two methods. So method 1, the graphical method. So step 1, draw sketches of each graph on the same set of axes, labeling the equation of each part of each curve. So I think you can do that now, and maybe you don't need to do two sketches this time. Maybe you can just sort of deduce what the graphs are going to look like from the start just by looking at them. With experience, you can maybe just jump straight to the answer on that one. So the blue curve, or the blue line, is going to be x minus 5. Or you could maybe just do it with a pencil and a rubber, because it's always good to draw diagrams in pencil in an exam in case you mess them up. So x minus 5 would normally look like that, crossing at minus 5. But we know that the modulus is going to reflect it. Get the straight line back again. So like that. So this is y equals mod of x minus 5. But there's something else I'm going to do here. I'm considering this part of the graph, which is y equals x plus 5. It's slightly different to this one. This is the reflected version. This is what I'm going to call the negative version of x plus 5, of x minus 5. So orange is the positive version of the graph, the unreflected version. And the left hand, the blue part, is the negative version of x minus 5. We've applied a minus sign to it to get that line. So this, in essence, is actually this one here, y equals x minus 5. And this one here is y equals minus, applied to x minus 5. We've reflected it. This is going to be useful in a little while, you'll see why. Okay, 7 minus x. Now I'll do it in a different colour for the purpose of this. I'll do it in green. Seven minus x. So 7 has a higher intercept. See it there. And 7, it's a negative gradient, a gradient of negative 1. So it's going to look like this. 7 minus x, but never goes below the axis. It's going to be like that there. And labeling each part of the graph. So this part here was the unreflected version. So that's y equals 7 minus x. But this part here is the reflected version. That's y equals minus 7 minus x. So we can see the solution is where the two of them cross. So step 2 of all this, by solving the relevant simultaneous equations, determine the value or values of x. So I can see here the equation that I want to solve is where my equation of y equals x minus 5, not the negative version of it, but the positive version of it, y equals x minus 5, meets this graph here, which is the graph of 7 minus x. So taking all the x's to one side, I get 2x on the left hand side equals 12, which means that x equals 6. And there we found it. And I think once you get used to drawing the graphs, this method is far quicker, far more effective than the next method I'm going to show you. I think it's my job as a teacher to show you as many different methods as possible, and you choose the one that works for you. So method 2. Squaring both sides. So let me just remind myself what the question was. X minus 5 and 7 minus x. So mod of x minus 5 equals mod of 7 minus x. So I'm sure you can guess what step 1 is. Square both sides. So the issue with modulus means that we don't know whether what's in the bracket is positive or negative, because by the time we see it, the modulus has made it positive. But there's one way that we know to guarantee to make a number positive, or at least non-negative, and that's by squaring both sides. Squared numbers are always not negative, so either 0 or positive. So let's square both sides to guarantee that both sides are positive and that the modulus sign is no longer required. And then you've got a quadratic to solve. I'm going to let you finish that and I'll do it myself in a little while. So solve that quadratic. Step 2, solve resulting equation. X equals 6. But there has to be an extra step when you do it this way, and I'll explain why in a short while. Step 3. Check answer in original equation. Check the answer in the original equation. So, the modulus of 6 minus 5 equals 1. The modulus of 7 minus 6 also equals 1, so we're done. But it's so important that you do this last bit, check the answer in the original equation. And as I say, the reason why, I'll illustrate it now. So for example, let's do the equation modulus of x minus 6 equals minus 2. So let's square both sides to get x minus 6 squared equals 4. Multiply it out, x squared minus 12x. I suppose actually it's in complete square form, isn't it? So we're in an easy position here to be able to solve it. So x minus 6 equals plus or minus root 4, which is plus or minus 2. Which means that x equals 6 plus or minus 2 equals 8 or 4. So we've got two answers, 8 and 4. Let's check them in the original equation. So the modulus of 8 minus 6 is 2. not minus 2. And the modulus of 4 minus 6. Well, 4 minus 6 is minus 2. Modulus makes it 2. Still not an answer. Both the answers we found here are invalid. And the reason I think the graphical method is more superior, because the graphical method would have shown us why those were invalid solutions. So, let's have a look. So the modulus of x minus 6, let's draw it on the graph. Looks something like that. And y equals minus 2 looks something like that. The graphs never cross. Therefore, there's no valid solutions, and we could have seen that from the graph. What solutions this squaring both sides method has found? If we continued the graphs, the positive and negative versions, it's found those solutions there, but those don't really exist because we've seen because the modulus sign. So squaring both sides method sometimes introduces extra solutions that aren't valid, and we've seen the mechanics of why that works now. So I think draw both graphs, label each of the positive and negative parts of the equations, then decide which ones to try and solve to get you the solutions. Now I'm going to move on and apply this to inequalities now. And as I say, there's loads of practice questions on the worksheet that you can have a go at on those, which I've uploaded to the live lesson area. I want to move on to modulus inequalities now. One thing that's different about my normal classroom lessons that I'm doing here, by the way, there's less time to sit and practice the work. That's something that you have to do after the lesson and just keep playing these examples back. So modulus inequalities. Let's start again with an example. E.g., let's say solve the modulus of x plus 4 is less than or equal to the modulus of x plus 1, say. So what this says, just annotating it, the graph of y equals mod of x plus 4, that less than or equal to means is underneath, is smaller than, is underneath the graph of y equals mod of x plus 1. Now I think for inequalities, the graphical method is the only way to do it. The squaring both sides method has many, many dangers, all to do with flipping inequality signs with negative numbers and such. So I don't really want to show you the squaring both sides method, because whilst it'll work in the majority of cases, there are examples in exams that I've seen where they do try and catch you out. So the graphical method, we should use that to be safe here. So let's draw both of these on the same set of axes. So it's basically the same process as the graphical method for solving an equation. So the graph of y equals x plus 4. And I really do think it's important to label these graphs as you go. You might be tempted not to, but that makes it all the more difficult later on. So y equals x plus 4, which will mod of x plus 4, which will look something like, let's say, this. So labeling the positive part, the unreflected part, y equals x plus 4. And we've got the negative part here, y equals minus x plus 4, the reflected part. Y equals x plus 1, so parallel line, but that crosses a bit lower, like that, and reflected. So here I've got y equals x plus 1, and the reflected part y equals minus x plus 1. And we see the point of intersection is here. And it's interesting, it's necessary to find that point of intersection. So we can see that point of intersection happens when the positive part of the blue graph hits the negative part of the green graph. So this is the reflected part of the green graph and the unreflected part of the blue graph. So y equals x plus 4, which is the positive part of the blue graph. We want that where that intersects with the negative part of the green graph minus x plus 1. So that implies that x plus 4 equals minus x minus 1. So 2x equals minus 5. So x equals minus 5 over 2 or minus 2.5. And this is the key point here. What I'm going to do, I'm going to divide this graph into sections through the roots. And this is like solving quadratic inequalities in a sense. So I'm going to divide it into sections through the roots here. Right down there. Now in this section, you can see that the blue graph is always vertically above the green graph. Anything to the left of this, the green graph is always above the blue graph. Well, the blue graph is y equals x plus 4, modulus. The green graph is y equals mod of x plus 1. So this is telling us we want where the blue graph is underneath the green graph. And that's this left-hand section here. Here we see, and all of this, no matter where we stand on the blue graph, it's always underneath. We've always got a bit of green graph over our head. So anything to the left of this point of intersection is relevant. Therefore, x is less than or equal to minus 5 over 2 gives us the relevant region. And that's what we have to do to solve these modulus inequalities. Squaring both sides will sometimes work and it won't work other times. Let's do another couple. Let's solve, let's say this one here that I'm about to paste on the screen. Let's solve that. Try and get that bigger. There we go. Ooh. Yeah, so let's try and solve that where x plus 2 is greater than 2x minus 5. So have a go at solving that using the method I've just shown you. I'll leave that up there so you can see. Take a few minutes. Okay. So draw both graphs on the same set of axes. So mod of x plus 2 be something like that. Being sure to label each section as you write it. So that's y equals x plus 2. And this is the reflected version, y equals negative x plus 2. Y equals 2x minus 5. So cross at minus 5 and has a steeper gradient as well. So it would normally cross at minus 5. But now doesn't, because it's been reflected. So it now crosses at positive 5. So I'll draw that a bit better. Like that. And that there. Okay. So now, and I'll label that, we've got y equals 2x minus 5. Then the unreflected version, y equals minus 2x minus 5 there. We've got two roots, there and there. So each of the positive and negative parts of the green graph cross the positive part of the blue graph. So to find the first point of intersection, what we're going to do, I'll take y equals 2x minus 5, and we solve that simultaneously with y equals x plus 2. So that implies that, get all the x's on one side, x equals 7. So that's one of the points of intersection. The next one, y equals minus 2x double minus 5. So minus 2x plus 5, this graph here, also equals x plus 2. Which implies, get all the x's on one side, we've got 3x equals 3, which means that x equals 1, like that. So, let's divide this, as we did before, into strips through the roots. Vertical strip there, and a vertical strip, do a better job than that, and a vertical strip here. So as we can see, 3 strips, one here, a narrow one here, and another one here. We want the strip or strips where the x plus 2 modulus graph is above the 2x minus 5 graph. So we can see here, no matter where we stand on the x plus 2 graph, it's always going to be underneath the green graph. Well, no matter where we stand on here, we always look up and see green graph. The bit where the x plus 2, the blue graph, is above the green graph is in this strip here. So the blue graph is always on top of, covering up the green graph. So it's this strip here that we need. Therefore, lies between the two values, 1 and 7. It's a single region, so warrants a single inequality. So between 1 and 7, the blue graph is above the green graph. Notice I've used strict inequalities because it was a strict inequality in the question. Much like here, I used a non-strict inequality because it was a non-strict inequality in the question. So, one last time for one more, I think, and then we'll finish. So last one. Just make sure that it's hammered home. Try this one here. Give me a few minutes to do it, then I'll go through it. So I think I can do a better job of drawing that actually. I'm going to start that one again. There we go. And labeling it y equals 3x plus 2, y equals minus 3x plus 2. The positive and negative versions of the graph. And we can see that the points of intersection we find when the negative of 2x plus 1, the negative of 2x minus 1, which is minus 2x plus 1, is equal to, well, the positive part of 3x plus 2, which means that 5x equals minus 1, which means that x equals minus 1/5. That's one of the points of intersection. Also, where the negative part of 2x minus 1 equals the negative part of 3x plus 2. Getting everything on the same side. X on that side equals minus 3. And there's the other one. Divided into strips. There and there. And we want where 2x minus 1, the modulus of 2x minus 1, the blue graph, is underneath the green graph. We can see blue is underneath green. In this strip here, everything to the right of the red dotted line, and looking carefully here, the blue graph is under the green graph there as well. So there's two separate regions now. So x is greater than minus 1/5, or x is less than minus 3. And if you're asked to do that in set notation, what you do, the set of all x values such that x is less than -3 united with x such that x is bigger than -1/5. Or in interval notation, -∞ up to 3 united with -1/5 up to infinity. 3 different ways of writing the same answer. And that's where we'll leave it. So have a look at the worksheets that I've put on in the lesson area and really have a good practice at those. And this recording will be up within an hour, so you can then have a go at replaying the different bits if there's anything you didn't understand. So thank you for coming along, and I'll see you again hopefully next week.